Yep. All right, here we go. Let's keep doing this integration practice. So the next question that I want to go over is the integral of x over x squared plus 1 dx. All right. So how would I do that? So after doing all those arctan problems, you might say, oh, this is going to be arctan again, but it's not because the top is not a constant. It's not 1, it's not 4, it's x. So that changes everything. So you're like, well, how do I do it? Well, it turns out we're just going to do a regular u sub here. So let's get after it. So what do we let u equal? So typically when we do a u sub, right, we let u equal that innermost function so that when we rewrite the integral, it's something that we recognize. Well, the innermost function here is maybe not as obvious to see, but it's going to be that denominator. So a lot of times with fractional integrals, we let u equal the denominator. Now, that's obviously not always true because the ones we were doing before, that wasn't the case. But in this case, it will help us to do that. So if I let u equal x squared plus 1, du will be 2x dx. So now I don't see 2x dx. I see x dx, and not a big deal. Just multiply both sides by a half. So I get a half du equals x dx. And now that's good stuff because I see a x dx right here. So all of that is now going to get replaced with 1/2 du. Now the bottom, in the problems we were doing before, we would let, you would have like u squared plus 1, but you're not going to have that now because you let u equal the bottom. U is all of that, right? U is x squared plus 1. So all of that is u. All right. So when I rewrite this now, I have the integral of a half du over u. Now, a half is just a constant, so that can get pulled out. So I get the integral of du over u, which honestly, I hope you recognize that, right? Do you know a function whose derivative is that? You should, but maybe for added video flavor, I'm going to emphasize or rewrite this as the integral of 1 over u du, right? They obviously mean the same thing. So do you know a function whose derivative is 1 over u? You should. The answer is ln absolute value of u. So then again, don't forget the 1/2 here. And then, of course, your constant of integration. So now you know what u is, right? We let it equal x squared plus 1. So we get the ln absolute value of x squared plus 1, and then, of course, plus c. Now, if this is a multiple choice, or maybe you were looking in the back of a textbook at the answer key, you might see that they didn't have the absolute value bars, right? They wrote it as ln of just regular old x squared plus 1. And the reason for that is because you don't need the absolute value bars anymore. Because if you think about it, if you have x squared plus 1, whether x is positive, 0, or negative, this will always evaluate to be positive, right? And so if it's always positive, you don't need the bars. All right, so initially you got to put them in because you don't know how it's going to play out. But as soon as you get to this point, you realize, okay, I don't need them. So this is it. So notice there's no arctangent in this problem. And so you're like, well, why did I include it in these conversations? Well, because if you look at the actual integral that you're doing, it's an awful lot like, looks a lot like these guys, right? Again, the only difference was the top was not a constant. It was a variable. Now, just for kicks and giggles, because I think this would be good review, let's actually check this, right? So I say all the time, don't lose sight of what it is you're finding. You're finding a family of functions differing by a constant such that if I took the derivative of this, I should get x over x squared plus 1. So let's go ahead and do a check just for fun. All right, so I want to take the derivative with respect to x of 1/2 ln of x squared plus 1 plus c, okay? So derivative of sum of the derivatives. The derivative of a half ln of x squared plus 1, that's going to be a constant times a function. So the derivative of that is just going to be the constant times the derivative of the function. Now, the function is a composition. It's ln of stuff. So the derivative of ln of stuff is 1 over stuff times the derivative of stuff, right? Stuff is going to be x squared plus 1. So the derivative of that is just 2x. And all that is the chain rule there. So now we can spruce this. Factor of 2 there goes with a factor of 2 there. And oh, by the way, the derivative of a constant is 0. That's why we always add it. And so then you end up getting, when you simplify this, x over x squared plus 1. And you're like, oh, check that out. I just found a family of functions differing by a constant such that if I took the derivative of it, I got what I started with. Okay? So nice little problem. All right, so let's rock and roll and let's kick it up. another notch. So what if now instead of x over x squared plus 1, so instead of this, it was actually this, okay? So it turns out if you do a U sub like we just did, this would pose a little bit of a dilemma. So then what do? What is the technique here? All right. The technique here is the following. All right. Whenever you have a polynomial divided by a polynomial and the degree of the numerator and the denominator are the same. So you're like, what are you talking about degree? Degree is the term with the highest exponent. It's that value. So the degree of the numerator here is 2. And the degree of the denominator, the term of highest degree, would be the x squared term. So it's 2. Whenever the degree of the numerator and the denominator are the same, it turns out that something that you're going to want to do, which is in your AB curriculum, is to long divide. So to long divide this, to simplify this expression. So I'm not going to do a U sub. I'm going to long divide. So real quick, let's just remember how we divide, right? So back in the day in elementary school, if you were doing like 7 divided by 2, you may have written 2 into 7, right? How many times does 2 go into 7? We put a 3 here. And then what would we do? We would do 3 times 2 is 6. We'd put that there. And then what would be the next step? We would subtract, right? And then get 1. And if we didn't know decimals yet, we would circle this because this would be our remainder. So this is my remainder, okay? The 3 is my quotient. The 2 is my divisor, the thing I'm dividing by. And then the 7 is the dividend. So now what does that mean? That means that 7 divided by 2, according to my work here, is quotient plus remainder over divisor. So it's 3 plus a half, which back in the day you probably just wrote as 3 and a half. Okay, but this, guys, means that. So now, believe it or not, it's no different when you are dividing polynomials. It's basically the same thing. So now if I want to divide here, just like I did here, I'm going to put the divisor down here, but I'm going to put what I like to call fillers in for terms that may be missing when I write it in standard form. So like x squared polynomial with degree 2, notice there's no x term. So I'm going to write 0x. You don't need to write that, but it tends to help you organize your work into columns properly. If you do, right? The superstar mathematicians in college, it's rare that they do that. I'm not a superstar. I'm going to write it. Okay. Now I'm dividing this into x squared. So again, especially here, I don't really need to put these fillers in, but I'm going to put them in. There's no x term and there's no constant. Okay. So now the way you play this little game, it's much like this, although I think of it slightly differently. I ask myself, hey, I'm going to look just here. So only look here and only look there. That's how you start this algorithm. What do I need to multiply u by in order to get u? And the answer is 1, right? So 1 times x squared gives me x squared. That's how I view this. And so now I put this in the constant column. If I would have got like, if I would have said, if this would have been, say, I don't know, x cubed here. And so what do I have to multiply u by in order to get x cubed? And the answer would have been x. I would have put the x here. You want to line up, as you do this work, all your x squareds in a column, all your x's in a column, all your constants in a column, right? It's basically analogous to place value here without getting too much into it. So now, what did I do when I put that value up here? Well, I did 3 times 2 and I got 6. Well, it's the same thing here. I'm going to do 1 times all of this, but obviously I have more than one term there, so I have to distribute. So 1 times x squared is x squared. 1 times 0x is 0, or I'll just for fun write 0x. And then 1 times 1 is 1. And I draw the line much like I drew the line here. Now, what was the next step here? We did the subtraction. You have to subtract it. So I have to subtract this line. So now I'm subtracting all of this, right? So some people will do minus and they'll do a parentheses here, which is fine because that's what you're doing. I like to say, all right, yeah, it is minus parentheses, but I'm just going to go ahead and distribute that negative right now. So in other words, this is minus, distribute the minus there, I'll circle it, distribute the minus there, I'll circle it. Some people are like, well, if you have plus, can't you just do that? Right? That's not a minus sign, people. That's a plus sign with a fat middle bar. All right? Just do what I did here. So now what do you got going on? So if you do it correctly, this first term is always going to wipe out. We got lucky before because this is all 0. And then you get -1. So you're done, right? So you stop just like we did here and circle this. This is your remainder, okay? The 1 is your quotient, and this stuff here is your divisor. So the algorithm is just like the one you learned in elementary school. This division, right? Much like the 7/2 was quotient plus remainder over divisor. Well, this division here is the same thing. It's quotient, which is 1, plus remainder, which is -1, over divisor, which I'm going to lose the fillers now because I'm done with my division, which is that. Okay? And that's it. This is equivalent to this. If you don't believe me, get a common denominator here and combine them. You will get that expression. All right, so put this over 1, multiply this by x squared plus 1 over x squared plus 1. There's your common denominator. Add the tops. Bam, you're going to get that. So now you're like, why'd you do all that? Well, because this I had no idea what to do. I tried to use sub. It was a disaster. I didn't like where it was going, right? So I do this long division thing. And now I get the integral of the sum, and the integral of the sum is the sum of the integrals, right? So the integral of 1, a function whose derivative is 1, that's just x. And then the integral of this, right, that first video, we did a whole bunch of those, right? -1 is just the constant. Do you know a function whose derivative is 1 over x squared plus 1? You do. It's arctangent of x and then plus c. And it looks a little weird how I wrote this, so I'm going to rewrite this as x minus arctangent of x plus c. This is a family of functions differing by a constant, such that if I was to do a check like the previous problem and take the derivative of it and simplify it, I would get that. So this is long division. So this is using long division to help you simplify an integrand so that you're able to do the integral. Believe it or not, this is in your AB curriculum. They don't always ask about this. They very rarely ask about it, but who the heck knows, right? Calculator's not required on this use exam. Maybe this is the year they drop it, okay? So pretty neat little question. All right, so I'm going to do one more question. So the video is going to be slightly longer. Actually, you know what? I'm going to end it. I'm going to end this video, and then I'll make one other video about something that is similar to all this stuff. So take care, be good.